I just wanted to mention that this meeting is recorded because of time difference. We wanted to make sure everybody would have the opportunity to view the meeting. Our first speaker is Dr. Moshe Delshad. She is a research professor at the University of Texas at Austin, and also she is a senior advisor at SimTech LLC. And she served as the vice president and 2013 to 2014, and the president and CEO 2015 to 2019 of Ultimate EOR Services. She was the assistant director of the Department of Energy funded Center for Frontiers of Center for Energy Security, CFS, from 2009 to 2014. She has over 35 years of work experience in modeling multi-phase and design of subsurface contaminant transport and remediation. She's done quite a bit of work in the area of CO2 storage as well as hydrogen storage. She has many publications in various areas, and she's done quite a bit of work in the area of development of computational code for various enhanced oil recovery. And as of late, she's been working quite a bit in the area of hydrogen storage. So with that, I hand it to Dr. Delshad.
Thank you so much, Kami, for the introduction, and Jijun for the invitation. So you see my slides now?
Yes, we do.
Yes, you're
Okay.
fine.
Perfect. Let's see here. Okay, so today I would like to share the results of a project that we did at SimTech for a company, for an operator, estimating the amount of carbon emission they have during their operations of 2 fields, and then coming up with the strategies, methodologies to reduce the emission to certain goal that they had by 2030. So first, I'd like to give you a little bit of background and statistics on the global CO2 emission by different sectors. And as you see, for 2019 emission, hydrocarbon extraction and power generation, they're the top 2 in terms of the carbon emission. And if we continue business as usual, by 2050, of course, we're going to have an increase in the emission from these 2 sectors. So if we are able to come up with the ways to reduce the emission, and the goal is by 2050, we reduce it significantly from the oil and gas operations and also for the power generations. So what are the emission sources in oil and gas operations? They come from exhaust gas, from engine, turbine, heaters, gas flaring during well testing. And even when you do CO2 EOR operations, you're going to have some carbon emission. And there are a lot of wells, they are abandoned or orphaned in some of the oil, the old oil fields. And EPA just recently announced about 130,000 well documented, but that doesn't mean that's a total orphan wells that we have in US as part of the oil and gas operations. So a little bit of background regarding the different classifications for emission. If you're not familiar with, there are these classifications they refer to as scope. And these, there are 3 scopes that would allow the companies to differentiate between the emission they directly create and they can control versus the ones that they actually contribute, but only indirectly. So scope 1 is the emission that are directly associated with the company's operation. For example, if you're in an oil and gas company, that comes from like the leaks for methane, flaring, and some of the refining processes. Scope 2 they're the ones that is beyond a company's immediate control. But they include emissions that associated with the energy used to power the operations. So again, both Scope 1 and Scope 2 should be considered by the operators to reduce the emission. Scope 3 is more associated with the consumption of the product. So for oil and gas, that happens with the transportation, combustion and so on. And currently, not many major oil companies are contributing to Scope 3, only a handful of them. But Scope 1 and Scope 2 are considered with a lot of operators. So how can oil and gas contribute to lower carbon future? There are different ways to do that. And it really depends on the countries, their approaches, their demand, capabilities, and culture. And through this energy transition, oil and gas will still remain an important part of the energy mix. You just have to look at the portfolio of energy. You cannot just completely abandon oil and gas. In order to meet the energy demand affordably and reliably, and also contribute to international climate agreement goal. So if you read a lot of the literature about how to tackle this lower carbon future, I highlighted 3 that are mentioned pretty much everywhere. One is renewable energy, that you be able to address resource strategies and shortages, and also climate change. Specifically wind, solar, geothermal. Carbon capture, storage, and utilization is going to have a vital role in lower carbon emission future. And this is something that we have the experience of doing it. Already there are case studies. We know geology, engineering, and we have the commercial scale expertise. There are existing pipelines, infrastructure. There are known geological formations that they can be used for transport and storing CO2. The third one is clean hydrogen. And that's fuel of the future, so-called, and very versatile. And a lot of publication, they describe it as a missing link in efforts to make energy system radially cleaner. It can have a lower cost than total electrification approach. And also you can decarbonize sectors that are very difficult to just convert to electricity. And there are ways to store and or transport excess renewable from hydrogen. So basically, if you have excess energy from wind or solar, then you can transport it, store it in tanks, subsurface, and then use it when you need it. And there's a way to continue to use gas network infrastructure. Of course, there are groups that are working on how they can blend the natural gas with hydrogen currently, and then the future is going to have an infrastructure that you can actually transport 100% hydrogen. So just a little bit of activities in CCUS and hydrogen in 2022, and giving you the capacity as a function of years in 2019 to 2022. Of course, you see the growth. But even if you look at the capacity, CO2 capacity by end of 2022, we're still about 8 times short of meeting the 1.5 degree scenario by 2050. So that means that we have to continue this growth in order to meet that goal. In terms of the hydrogen and the capacity based on the projects up to 2022, there are 2 types of projects. The green is the one that you actually use the electrolysis, and the blue is the one that you use from the power plants, so-called blue hydrogen, but including CCS part of it. So that is also considered clean hydrogen. And again, you see the growth, but we're still 7 times short to meet the 1.5 degree scenario. So the project that we did for this operator, the objectives were to identify major sources of the field emission. And we basically focused on two fields in their operations onshore, and propose carbon emission reduction methodologies, and then conduct detailed calculations of carbon emission reduction. So this is really sort of like your executive summary of the project that we completed, looking at the emission sources from the scope 1 and scope 2 drilling operations, and also looking at the possibility if they have any flaring. Of course, this operator specifically said they do not flare any gas. And then our strategy was to recommend alternatives for efficiency improvement of the existing diesel generators, heaters, equipment by retrofitting, and also evaluate massive electrification. So converting the diesel generators to electric generators and using the imported grid power. So the power was imported to these field operations. Propose green power integration, so renewable energy sources, and then ultimately look into the CCUS. So injecting CO2 in oil reservoir that they can produce additional oil, but at the same time sequester some of the CO2. This will be the summary, and you see at the end that I'll go through step by step of how we got to this point of looking at the CO2 emission in kilotons as a function of years up to 2030. That's where the goal was, to reduce the emission from the base of 2019, 2020 to 2030 by 25%. So we show the amount of emission. The blue is at the bottom, is from the drilling operations. And then the gray is the central processing plant emissions. I will talk about this in more detail. And then the orange is the total. And you see how that changes over time, pretty much, stable. But then they had planned from 2027 to 2030 to increase the capacity. And that's where you see the additional, especially from the electricity requirement that increased significantly. And the dashed yellow is our target. So we want to get to this level of emission to meet the 25% reduction goal. So we had to go, step by step, collecting data from the operator, and also look at the published calculations, analogs, to be able to complete this project. So the workflow started with looking at the CO2 emissions for scope 1, and then electric consumption converted to CO2 for scope 2. And then you're looking at the total carbon emission, and then be able to back calculate the emission for each of the processing or production plants, which they had 2 of them. So quite a bit of a detailed calculation. I don't have time to do that, but just show you the summary that at the end of our calculations for the emission, we came up with the scope 1 and scope 2 as a function of years up to 2026 before we get to the expansion of the facility. So for the scope 2, everything is done in power units, megawatt per hour, and then we had to convert that to equivalent CO2 emission in kilotons. So if you compare scope 2 versus scope 1, you see major carbon is coming from scope 2. And then we had to extend our calculation to 2030, and that's where you see the increase, especially in the scope 2 emission for the development of much larger activities in the field. And once again, they had two central production units, 1 and 2, and then we had to split the amount of emission for each of these plants. And they also were looking at it in different phases. So we have to break it down into different scopes, different phases, and also different production facilities. And once again, if you look at the details, at the end, we end up with 83% for scope 2 emission, 17% for scope 1 emission for both production facilities. Most of the information we had to collect in order to do the drilling operations, the drilling rig operation was really coming from the operator. They had to provide us this information regarding the rig that they were using, and then for each of the section, what is the diesel consumption, and then we had to calculate it per well, the amount of diesel, calculated based on emission, and then come up with an average of total rig year for field development, because everything is going to be based on number of years that the rig is in operation. So just giving you a little bit of information as how you build this data is, first you have your rig number, and then you decide. Here we assumed 2,000 horsepower for the rig. And then for each well, you do your calculation. This specific well belonged to the central production plant, number 1. So for drilling section, you have different, hole sizes for different depth, casing sizes, how long you've been doing this drilling, how many engines were used, and the depth. And then from this information and the information provided by the operator, you can estimate the daily consumption of the diesel in US gallon, and then estimate the total consumption. So for this case, we ended up with about 45 days of drilling operation, and about 290 to about 300 tons of diesel consumption in 45 days. And that is about 1.5 million kilowatt hour for the 2,000 horsepower rig. Then we had to split the information to 2 different fields and the rig years for each of them. So we had to convert the diesel consumption per year of rig, and then ending up with the numbers that gives you the total per rig year, because we need that in order to split the information for the 2 fields and per year. So we have diesel consumption, we have electric consumption, and then the total carbon emission from the drilling rig operation. So that's what we ended up with, these 2 graphs in a simple way. Field A, these are rig years. Blue is for the new wells, and gray is for the workover, the amount of time that the rig is in operation. And we did the same thing for field B. So then total rig for the drilling for both fields is about 4 years, for example, in 2020, but it can go to almost 8 years in 2028 when they do the expansion. So it really depends on, the activities in the field and the wells and so on. Then we estimated the consumption. So now that we have the information per rig year and we know how long every year the rig is in operation, we can come up with the estimate of the emission. So for example, during the drilling operation, the CO2 emission from diesel in kilotons, going to be these numbers in the second row. anywhere from 31 kilotons to maybe 70 kilotons. And then the amount of emission from by electricity. So if you convert your diesel to electrical, of course, you still have some emission, but you reduce the emission by electrification. And those are the numbers here. And the difference between these two going to be how much you reduce the emission just because of your drilling operations. And this graph basically shows you those numbers. The purple is going to be the amount of emission by the drilling, and the orange is going to be how much you reduce it by electrification. That is about 38% overall. So now going back to the graphs I showed you at the beginning, this is what we ended up with in terms of the drilling operations, how much emission we have at the bottom. And then we have the, if you use the gray color is from the central production plant, and the orange is going to be total. So that is going to be your total emission over time. So now our approach was how we can reduce this emission to by 25% by 2050. And the only way was to consider an integration of renewables, renewable energies, and CCUS. So our strategy was to recommend alternatives for efficiency improvement of existing diesel generators. So start in a more low-cost approaches, but still you benefit from reduction of the carbon by retrofitting your existing equipment, but improving them. And then massive electrification. So converting your diesel generator to electric generators. And this is based on importing the power from outside. So this is not within the field operations. Propose renewables, and then also design CCUS. And specifically for this operation, the operator was interested in CCUS, so using CO2 that is captured for enhancing oil recovery and then storing some of the CO2 as sequestration. And of course, we will talk a little bit more about this, but there are different methods for green energy, geothermal, solar, hydrogen, and wind. And then for CCUS, again, this operation, we're interested in depleted oil and gas reservoir, but then if there is aquifer available, that can be also considered for storage of CO2. So then we had to come up with a roadmap to be able to meet the target from 2019 to 2030. So first is the initiation plan that may take 4 or 5 years. And during this time, I think we propose to replace the diesel generators. And then for the scale up, electrifying the rigs. And then when you get to the deployment, that is going to be like 2029 to 2030 when you start deployment, then electrifying the rest of the platform equipment, like the compression system, logging, cementing, and the heating, and so on. And for production facilities, for the initial phase, we proposed equipment optimization. So making sure that you detect the leak, you make repairs to minimize or completely get rid of the leakage, and installing vapor recovery units. So then you can actually use that flared or leaked gas. Regular maintenance and replacing of existing equipment, and reducing non-routine or routine flaring that may happen in the field operation. And then for the scale-up, we talked about possibly looking at the gas turbine generators, solar energy, geothermal, and then some hybrid green energy. And then ultimately for deployment, expanding your power sources, and that can come from offshore wind, can come from hydrogen, or some of it optimization of your CCUS. So I'd like to share with you some of the projects that we looked at as analog for renewable energy that can be implemented in this specific operation that we worked on. There is a very large activity in Texas, in USA, is called Goldsmith Solar Field Project, that they can actually project it to reduce the carbon footprint by over 20,000 tons annually. So these are all PV solar panels. A project in Oman, Mira project, referred to as Glass House, they've been using the solar to generate heat for their steam flooding projects for oil production. And they have almost capacity of 6,000 tons of solar steam per day. And they expected to reduce the emission by 300,000 tons annually. A geothermal project in Alaska, in USA, that they're using a relatively low temperature of hot spring is about 75 degrees C, and converting that temperature and using it in the, the ORC for power generations. And right now the capacity is up to 40 megawatt per generator. Some of the other projects, one in Norway that they've been using the wind offshore, and they have about 88 megawatt capacity, 11 wind turbines. And the projection is they can offset about 200,000 tons of CO2 emission. And this actually is off of Gulfax. I worked in that field several years ago with Statoil. Japan, they have a hybrid power generation where they use 100% ammonia in their gas turbine. So then when we considered these strategies, one for the equipment optimization, the other one for electrification of the platform, we ended up with these reduction estimates. So for example, here, if you do the completions of wells using a green energy, you reduce 2.6%. But overall, you see these are pretty small percentage in terms of the reduction of carbon. And for electrification over years, pretty steady, but about 4.8%. So we're not going to be able to achieve the goal of 25% this way. So then another strategy was to use the green renewable, and we looked at the literature of how much reduction you are going to have in carbon emission for each of these renewable strategies. And then we did some calculation and estimated the reduction for this specific operations. So for example, here, over years, you see with solar about 3.8%, and then if you combine solar and thermal, about another 3.8%, offshore wind 7.6%, hydrogen about 9%. And of course, these are the technologies that they're going to develop over time. So initially, we didn't put much of emphasis, for example, on hydrogen or wind till 2029 and 2030. I like to mention one very large project in California, and that is called Solar Lost Hill project, that they produce 1.4 billion kilowatt hour of clean solar energy, and they're reducing the carbon emission by about 1 million tons. So now if we include some of the equipment optimization in our chart that I showed you before, this is now the black line is how much we can contribute and reduce the reduction, reduce the carbon emission by just equipment optimization. If we include renewable, solar and some hybrid, then we're going to reduce it even further, but still we're off quite a bit from our 25% target. And now if you include more of the renewable sources without CCUS, so now we're not including CO2 capture and storage part of this scenario, just looking at flaring reduction, electrification, hydrogen, and so on, we end up with some decrease, but again, we're off from our target. So our conclusion was the only way that you can meet that 25% target by 2030 was to include carbon capture and storage and utilization potentially. So I'd like to mention to you about activities of CO2 capture and storage projects around the world. In 2017, in terms of the capture, there were 10 projects with a capacity of about 25 million tons per year, and 16 projects with 32 million tons per year, and dominantly they were EOR projects. So that's in 2017. And 2022, these are some existing projects and the ones that they're planned. So when you see that there is a FID, that's where they're doing the final investment decisions. And that's a combination of the capture, storage, direct air capture, DAC, hydrogen, which is blue hydrogen with carbon capture, still considered clean, and then green hydrogen. So this is the activities in 2022. And just last month, there were two big announcements from two companies. One, Chevron, that partnered with other companies, including PetroChina, and they signed an MOU that they're going to evaluate advanced development of larger scale carbon capture, utilization, and sequestration in Singapore. And they are going to consider capture, storage, and utilization in not only for EOR, but also for other targets of plastic, fuel, and cement, and so on, and including transportation. Wintershall awarded a CO2 license in Norway. That happened in October 5th. And that is going to be close to Bergen in Norway. And they estimated that they can hold CO2 up to about 5 million tons per year. And there's going to be also a hub built in Germany that they will capture and transport CO2 for storage to Norway. So part of our project for this operator, at the end, we did not have access to their detailed geological models for the two fields. So we couldn't do really good assessment of the capacity of CO2 in these two fields. So when we decided to do very simple volumetric methods or use the type curves that they exist based on all the CO2 EOR projects that been done in the past. So we did propose two methods based on the pore volume of the reservoir and how much oil in place they have, what is the average oil saturation at the time that we want to consider CO2 EOR, estimate some residual oil saturation, and then came up with a volumetric estimate of the CO2 capacity. for each of the fields. So these are the numbers that we came up with. Another method was based on the type curves that they are published. Actually, Dr. Lake from UT Austin, he has this paper that we used talking about how much CO2 you're going to retain in hydrocarbon pore volume as a function of how much CO2 you injected. So of course we have to make some assumptions here as how long they're going to do CO2 injection for the EOR purpose. So we use the average curve here, and there are other ones with the 1 standard deviation and twice standard deviation. And we came up with these numbers. For the field 1, actually, interestingly, they were very close, the two estimates. But for field 2, they were drastically off. But again, these were just the initial estimates of contribution of CO2 storage for carbon reduction. So I'd like to mention to you that there are different methods of estimating the CO2 capacity in subsurface. And some of the challenges with CCUS and CCS estimate of capacity is really, well, projects is the injectivity, very hard to predict, capacity, and containment. And these are some of the results from a Department of Energy and also USGS Geological Survey, that they estimated the amount of CO2 stored in saline aquifers and in depleted oil and gas reservoirs in the US. So two different estimates. The dark is from the Department of Energy, blue, and the light blue is from USGS. And they did 3 scenarios, low, average, and high, and you see the differences in the estimates of capacity. And they did the same thing for just the depleted oil and gas reservoirs and estimating the capacity. And again, very different estimates. And one interesting observation here is saline aquifers, they can provide really the largest storage capacity compared to oil and gas. Basically, the estimate here is less than 10% of total. And then just trying to emphasize that it's really important to do numerical simulations, include the heterogeneity, include some of the constraints we have for the injection and building up pressure in the reservoir versus these simple static estimates. And these are showing you, again, from the USGS, if you just do static estimate of capacity of CO2 versus if you do numerical simulations and do a dynamic, almost 6 times lower than the upper estimate for the static. So we really need to do numerical simulations, include the heterogeneity and so on, the constraint on the cap rock to come up with the better estimates. And this is a project that was done in Norway for CCS. Initially, they wanted to inject CO2 in this formation, but then they ended up building up pressure, and they stopped the injection in this after injecting about 1.1 million tons, and they moved the injector into the upper zones. And since 2008, they've been injecting in this formation for the total of about 4 million tons. These are some of the activities on hydrogen, on production, storage, and also for blending of natural gas and hydrogen for the pipeline transportation. So in summary, for the projects that we did for this company, our decarbonization workflow included options to develop plans and technologies to meet the 25% emission reduction target by 2030. Critical data from drilling, subsurface, production facilities were first acquired from the operator, and then followed by an assessment of current power consumption and demand from existing drilling and production facilities. Scope 1 and Scope 2 CO2 emissions were analyzed, and then we explored renewable energy and with potential to decarbonize the field, and of course the CCUS, and then we presented a roadmap to achieve that 25% goal. So with this slide, I conclude my talk, and thank you so much.